Hi, I'm Igor, and what you're looking at right now is an artificial intelligence I made for detecting and classifying players in CSGO. It uses technology very similar to that of self-driving car cameras and other applications that require robots to see. If you just want to see it working and maybe watch a quick recap of everything at the end, you can skip to this timestamp here. All major parts of the AI's construction are also timestamped, so feel free to skip around and watch whatever interests you. However, if you're new to AI, machine vision, and convolutional neural networks, you may want to consider watching the whole process, as some parts of the video have very nice intuitions behind them, and I just think it's fun to watch in general. The project's documentation is on GitHub, link in the description. Thank you very much for watching, and enjoy! Okay, so first things first, we have to decide exactly what the hell we're gonna do. Here's the plan. First, we don't want the AI to have any sort of advantage that a player wouldn't, so no access to memory, files, anything like that. We're going to capture the screen, and that'll be the only input the neural network will have to work with. So after passing the screenshot of the game to the AI, we'll hopefully receive the enemy's locations correctly, and then we can use these coordinates to fire up a simple Python script that'll emulate mouse movement to adjust the character's aim to the correct location. I should also mention at this point that to make the AI's job a little easier, I'm only going to train it using images from the most popular, beloved, and hated CSGO map, Dust 2.
Part 1. Capturing the screen.
Alright, time to get to work. So, for capturing the screen, we're going to use a library called MSS, which is just a really fast framework for taking and processing screenshots. Thanks to Sentdex for already making this pretty neat code block that does it all in one go. So now, we should just have to align the CSGO game window with the top left corner of our screen, and hope the images start rolling in. And as you can see, there they go. We now have a constant feed of screenshots from the game that we can input into the neural network.
Part 2. Creating a dataset.
Now, no matter what type of AI we end up creating, we're always going to need data. Trust me, in machine learning, data is king. It doesn't matter how good your algorithms are, if you don't have enough data, you're not getting far. That's why companies like Google and Facebook like to squeeze every little piece of data they can out of you. You know those captchas by Google, those I'm not a robot things, where you need to say where street objects like hydrants and bikes are? Well, guess where that data is going to? Oh yeah, also, you know how Facebook and Instagram indirectly favor posts that have hashtags on them? Can you guess why that is? You see it now. The internet is a giant labeling center. So how about our data? Well, this time we want to train the AI using supervised learning. But then of course, what is supervised learning? The idea is that we're going to have a list with a bunch of examples. That'll be our dataset. In this list, each example is its own little list of two elements. First, there's the actual data that we want the AI to look at, and then there's what we call the label, which is kind of an answer sheet where we'll state the correct or optimal answer for that specific example. Later in the video, I'll explain how we're going to compare the label to the AI's answer in order to make it learn. So in our case, we want the data in each example to be a screenshot that contains one or more players in it. Then, the label will be a collection of the coordinates and classes of each player on that image. Okay, so now we know exactly what we want. We want to create as many of these labeled images as possible. But now we need to find out how we're going to create those. There are two main ways for doing that. You can either manually grab each frame and write the labels yourself, or you can write some sort of program that will automatically create labels for you. Early on, I imagined that I would be able to label enough images by myself, so that's what I did. I adapted the screenshotting code we had made earlier so that it would save the game's screenshots to a folder and started playing the game. Playing the game was fine, but labeling took way too long. After listening to many podcasts, I stopped at 10,000 images, labeled by hand. Hoping that it would be enough, I gathered my stuff and started working on the actual AI that would soon receive that data.
Part 3. Convolutional neural networks.
Alright, so it's finally time for us to build the AI. So let's begin. So when talking about AIs that can process images, we're mostly talking about CNNs, which stand for Convolutional Neural Networks. Now, if you don't know what a convolution is, that's not a problem. I'll explain it in short right now, but I'll also leave a card here to wonderful mathematician and YouTuber 3Blue1Brown if you want to know a little more about it. But anyway, what's a convolution then? Well, in image processing, you can think of a convolution as the interaction between a matrix and a kernel. So right now, there's a matrix, there's a kernel, and there's this weird interaction called a convolution that receives these two entities and outputs another one. Most people understand matrices as these tables, where you can have coordinates and each individual location on the table has a specific value. That's great if you're using black and white images, because each pixel then only needs a single value from 0 to 255, where 0 is black and 255 is white. But when you're messing around with colored images, you actually need 3 different values for each pixel, because they're RGB, red, green, and blue. So actually, for each image, you're gonna need 3 matrices of the same shape bundled together. This bundling of matrices generates what we call a tensor, which is just a matrix of higher dimensions, like this. Okay, so that's the matrix or tensor part of the convolution. Now what about the kernel? Well, the kernel is just a smaller tensor of equal or lower number of dimensions than the input tensor. So if your input tensor has, say, 3 dimensions, like our image, your kernel could be 2 or 3 dimensional, and it's also normally of a much smaller size than the input tensor. Now, each of these is a kernel, but they all perform different operations over the input. The thing is, depending on what numbers you choose to put inside the kernel, different information from the input will be highlighted or transformed. For example, if I convolve around this image with this specific kernel, the image will be blurred. If, on the other hand, I use this other kernel, the edges of the image will be highlighted. Kernels can do very specific operations, like highlighting only vertical edges of an image, or maybe horizontal ones. But the key thing is that kernels are great at highlighting patterns. In a minute, we'll talk about why these kernels are an essential part of machine vision and AI. But first, I want to tell you really what's the hidden operation that is joining the input tensor in the kernel. And here it is. In this example, we're using a 5x5 sharpening kernel, a kernel that sharpens the original image. The idea of the convolution, then, is that we're going to slide the kernel through the image and multiply the pixels beneath the kernel by the kernel's own values. It works kind of like a filter, and this is what generates the output tensor. I won't get into the details of why these multiplications yield these results, but you can think of it as if they're creating an image where each pixel, when being created, took into account the other pixels around it in the input. This is one of those things that are like riding a bicycle. Once it clicks, and you can't forget how it works. So now we know the basics of convolutions. But what does that have to do with neural networks? Well, the thing is, I've said before that convolutions are great for highlighting patterns in images, and that's exactly the kind of abstraction that we need to extract and process information from the image. For example, if we wanted to make an AI for tracking someone's eye position, at first it may seem pretty daunting because there's just too much information packed together. There's color, a bunch of complex shapes we would need to take into account, etc. But if we apply some convolutions to the image, look, although there is less information, we gain clarity. And it's now easier to identify the patterns that we're interested in. So a big part of the AI will learn to dial in those kernels in order to extract the most interesting information possible. So in this case, the AI would have to learn which kernels, when applied one after the other, would generate these clearer images, called feature maps. This was a pretty simple example, and it's important for me to tell you that for the majority of cases, Not only does the resolution of these feature maps get reduced dramatically, but also, with each layer of the CNN, the feature maps become more and more abstract. So while at first, they might represent a pretty clear feature of your subject, like headlights or wheels in the case of a car, they quickly become surreal images with no correlation to our human mind's understanding of that subject in question. There is only one more thing I need to tell you about before you can finally start training the AI, and that's the loss function. You see, when people in AI refer to losses, they just mean the score that represents the AI's performance. Usually the lower the loss, the better, but that's not always the case. This is important because the AI needs to constantly know how well or badly it's doing in order for it to adjust its parameters and fine-tune those kernels. There are so many different ways for calculating losses for different types of problems that it would take me a lifetime to cover all of this in one video. So we're going to focus on two. First, let's talk about the intersection over union loss, or IOU for short. This loss is used when you need to put bounding boxes around objects, so that's going to be exactly what we need. So let's say we have an image, and this is our desired bounding box. And this is what the AI said that the bounding box should be. How should we assign a number that best represents how correct that bounding box is? Well, how about dividing the area beneath their intersection, that is, the area where they overlap, by the area of their union, their areas combined. It turns out this is a pretty great approximation for what we're trying to do. When both boxes overlap perfectly, the score is 1, and the less they overlap, the smaller the score gets. While training our own network, we'll actually use a slightly more advanced version of this loss called generalized IOU, and you can read more about that in the links in the description. The other type of loss that we're going to use is called cross-entropy loss, and this is used for when we need to classify objects, just like when we need to classify players as terrorists or counter-terrorists, CTs or TRs in the game. So let's say our AI returns that it's 80% confident that this image is a TR, and 20% confident that it might be a CT. If the image were to actually be a TR, then the best possible answer would have been 100% TR and 0% CT. So what the cross-entropy loss will do is that it will put the AI's answer regarding the correct label in a logarithmic scale, like this. So if the AI said this was a TR with 100% confidence, it would receive the maximum score of 0, and as the answer gets less and less confident, the loss gets infinitely bigger. Cross-entropy and IOU are two types of losses that we'll use, but all losses have a common property that I need to discuss with you: the idea of convergence. Inside the AI, there are a bunch of numbers that represent those settings I told you earlier about. The kernels, a bunch of other values that govern the relationships between neurons. But for a moment, let's imagine an AI with only two parameters, theta 1 and theta 2. And we'll judge this AI using our cross-entropy loss. We know that in this loss there is a maximum score of 0 that we're trying to achieve. So out of all those possible theta 1s and theta 2s, there needs to be a combination that will get us as close as possible to that perfect score. And that's our goal, finding the combination that will minimize the loss. Now here's a big insight that will allow us to visualize that. I want you to imagine a graph where the axes correspond to theta 1, theta 2, and the loss, just like this one. Each point in this gradient corresponds to a possible combination of theta 1 and theta 2, and the altitude of the point corresponds to how low or high the loss is at that point. So naturally, we want to find the combinations that lead us to these points here, the minimus. Let's take a minute to explore these ideas for ourselves before I just tell you everything up front. Close your eyes and imagine you're an explorer, an adventurer, trying to find an ancient treasure that you've been told is in the lowest valley in the Great Forest. When you try to scout the terrain using a helicopter, you realize there is a dense mist that covers the entire region, and you can't see the ground, so you have to enter the forest and try to find the treasure from the inside. You drop from the helicopter at a random location, and you are now amidst a majestic forest, with no sense of direction whatsoever. Oh, and because of the mist, you can't see anything more than a meter away from you. The question is, What would you do to try and find the treasure? Well, maybe the best guess you have at this point is just to follow whatever direction has the steepest downwards slope. After all, we're trying to reach a valley, right? The story you've just imagined is very similar to what we do in training AIs, something called gradient descent. When the AI first starts that training, they are dropped off at a random location with random parameters, and they need to find its way to the best possible valleys. So in a sense, the AI is just like the explorer, but instead of feeling the ground with their feet, they calculate the derivatives of where they are standing and move towards whatever direction is steepest downwards. Now, it's time for us to start thinking about the actual AI that we're going to use. There are many different architectures that are known to work well for this task, and each of them has a specific trade-off between speed and accuracy. The first one I tried to use was a network called Faster RCNN, and tried to train it using our 10K dataset. But there were some problems. First, it was really slow to train. I have a GTX 1060 Mini with 3GB of VRAM, and that thing was running for way too much time for just one training cycle. The second thing, and the more important one, is that the Faster RCNN was underfitting. That basically meant that it stopped learning after a while. See how our loss just basically becomes flat? That's because the AI isn't converging anymore. So how do we fix these issues? In regards to speed, I decided to use another architecture called YOLO v5, which is a network designed for mobile use, so it's super fast and ultra light. And we're also going to use the cloud. Regarding the underfitting, well, part of it may be reduced because of the new, better architecture, but ultimately, we were just going to need more data. And then comes the question, how are we going to generate more data, knowing that I don't want to draw even a single bounding box more? Yeah, you guessed it. Let's make the auto annotator.
Part 4. Infinite data.
So I sat there and thought to myself, how am I going to extract the position of players in real time, draw bounding boxes around them, and output those coordinates so I can use them later? Then it hit me. I don't need to code half of that stuff because there's already an entire community of super dedicated people doing exactly that. And they're hackers. Seriously, think about it. They make software that draws bounding boxes in real time, and all I need to do is modify some code so that the software outputs the coordinates for me. Now, just as a disclaimer, I despise hackers who cheat in matchmaking and public matches just as much as all of you. So after a bit of digging, I decided to use a software called Osiris by Daniel Krupinski, forked his project on GitHub and went to work. This cheat has a ton of features, so it took me a while to orient myself inside the code. After a while of searching and following different paths, I found exactly what I was looking for. So basically, in this software, there's this big structure here called game data, and inside of it, there are a bunch of different lists called vectors. Here is you, the local player, in this vector called local. And this is what we want, the player's vector. This is a list that contains the information of every single player in the match, except us, of course. And if you take a look, for each player in the list, there is a player data structure associated with them. But this data structure inherits from the base data structure. And if you look at that, you see that every single entity in the game is obligated to state its distance to the local player and the coordinates of their bounding box. This is perfect, because then I only need to write these coordinates to a text file and be done. So I wrote the code, and the output file ended up looking something like this, where each line represents a different bounding box. This being the index of the frame, this being the local player's team, where 0 is TR and 1 is CT. This represents if the player is an enemy from the local player. So if the local player were to be a CT and this box were to be a TR, this would be 1 because they're enemies, and it would be 0 if he were also to be a CT. These last 4 values are the actual coordinates of the box in 2D. There was only one problem. How would I know which bounding boxes corresponded to each images that I captured? After all, I need the images to correspond with the bounding boxes so I can make my dataset, right? After a while, I decided that instead of trying to make a sophisticated integration software that synced the capturing of the images with the game's internal clock, I would just write the current operating system time together with every bounding box. So that way, I knew which bounding boxes were taken together and at which specific times. The images I was recording were also named after the OS time. So I made up a Python script that checked for the closest bounding boxes to the image within a certain threshold. And it worked pretty well, raking in about 120 annotated images per minute. After some time roaming in deathmatch, making sure I always played equally with both TR and CT, I managed to gather around 100,000 labeled images, which is a pretty good dataset size.
Part 5. Training on the cloud.
So we have our dataset and we have our network's architecture. All we have to do is kick our network down the gradient and let it converge. Now, I could train it on my own PC, but as I've said before, I only have a 1060 with 3GB of VRAM, so it would take me way too much time to train it with 100,000 images. Thankfully, Google's GPU cloud service offers a free trial. And believe me when I say that I used that free trial to its absolute limit. It took me almost 24 hours to upload the entire dataset, but after it was done, it was game time. I ran many training sessions, tweaking the hyperparameters each time. These hyperparameters are things like learning rate, which dictate how big each step of that gradient descent is, the number of epochs that I trained the network for, and other things that I won't touch on in this video like momentum and dropout. These are the parameters that I can't change after I start a training session, and it's very important to get them right.
Part 6. Test drive.
I downloaded the weights, imported them into the code, and started playing around with it. It was identifying enemies pretty well, but sometimes it would classify them wrongly, like saying that a TR is a CT and vice versa. So I actually went ahead and trained the second AI whose sole purpose in life was identifying if an image had a TR or a CT in it. I used the same dataset that I used with the bigger AI with some minor changes to make it faster. So after training that and integrating it into the code, now I had both AIs ready to perform. And I gotta say that it worked pretty well. It isn't flawless by any means, it still has many errors, but it's good enough.
Part 7. Recap everything, let's go home.
So in a really fast recap, what did we do today? We first created a constant flow of images from the game, recorded 10,000 of those images, annotated them, and that was our first dataset. We then fed those images into the first neural network architecture, FastRCNN, but we saw that that didn't work well and it was too slow for us to use. So we switched the architecture to YOLO v5, which is more modern and made for mobile use, so it's much faster. In that time, we realized we were going to need much more data. So we reverse engineered the cheat software for CSGO and made it output the coordinates of the bounding boxes of every player in real time. We then created a Python script that would synchronize the recording of the images with the bounding boxes that we were obtaining through the cheat software. With almost 14 hours of recording gameplay, we reached 100,000 annotated images. And so after 24 hours of uploading it to the cloud, we could finally train our AI. We trained it many times, tweaking many parameters that would influence how the network learned. After it learned enough and converged to a sufficient gradient, we took the network's weights and biases out of the cloud and into our own machine, so we could test it out. We realized that while detection was great, classification could still do some work. So we created a second AI whose sole purpose in life was to determine whether an image contained a TR or a CT. And after training that and integrating that into the code, we had our final product. Our baby was born and we had a CSGO detector and classifier. We then tried to feed these network results into our Python script that could emulate mouse movement. But we saw that that just wouldn't be possible. The only methods that could still be used to manipulate mouse movement in CSGO were way too slow, and the good methods that had low latency had been patched or just don't work anymore. So after coding all of that, getting stressed because of bugs, fixing those bugs, making it work eventually, writing some documentation, putting the code up on GitHub. I spent a whole month stressed out trying to make this video the best I can for you guys. And I know it's not perfect, it's not meant to be, but I hope you enjoyed it, because it really was made from the bottom of my heart. So thank you very much for watching. I really hope you enjoyed it, and I'll catch you up later. Thanks. While I'm here, a special thanks to Paulo. He's a researcher that led me through the process and taught me a bunch. I really couldn't have made this without him, and I'm very grateful to have him around. Thanks, Paulo.